And I appreciate the invitation. I haven't been to Stanford for about 7 years, and it's amazing how much money you folks now have. I almost got lost, and I, at one time, actually knew where this building was. But there's a lot of new construction, and it's no doubt a testimony to all the wonderful science that's being done here and the local billionaires. Having said that, I want to ask you something. Think about what you think about the deaths of massive stars. What is your mental picture of how they explode in supernovae? The core becomes a Chandrasekhar mass, it collapses, star has evolved for 10 million years. In seconds, that completely changes, the blast wave moves out. But what is your mental picture of how a neutron star is born? What is your mental picture of what's happening in the interior, in the belly of the beast? What's your mental picture of how black holes form, stellar mass black holes? Just give it a few seconds. I don't think anyone in the audience is right. I'm going to try to prove that. Now, since this is a technology place, I write my own laser. And so hopefully this won't bother people. I have to give credit, of course, to my collaborators, in particular Tianchu Wang, David Vartanian, David Radice, and Lila Choi, who is a junior. We just published a paper in Astrophysical Journal Supplement on gravitational wave emission from supernovae. I'll talk a little bit about that in the end if there's time. And I'll acknowledge my paymasters. So the supernova, of course, is an interesting phenomenon. There are many pictures of these things. They're very photogenic. This is 87A with rings around it, and the blast wave has hit those rings and caused it to emit. But I just want to call your attention to that central region. That thing is not a sphere. This is Cas A with X-ray and optical data superposed. This green is X-ray emission from iron. And the iron was produced in the belly of the beast again. It was produced in the explosion. And it's not being ejected spherically. What I'm going to show you and hopefully demonstrate to you is in fact that the explosion itself is very aspherical, fundamentally. Oh, this works. Okay, this is the same thing where these are different elements. And there are complicated distributions here. Again, the iron is being sprayed out. Why is that? It was produced deep inside in something the size of Stanford. Well, Stanford plus Palo Alto plus Menlo Park. And it emerged into something that was the size of Jupiter's orbit. This is one of my favorite little videos. This just cycles through from Detlef Hartmann. This is the crab. And you see the radio emission from, you see the emission from the crab itself, and then the debris. These things are evolving still. And so I'm going to give you, most of the talk is going to be mostly eye candy. But there's going to be some physics. And then there's going to be some words. And this is the word part. There are a few slides like this. And so what's new? What's new is we can do many simulations, bringing together all the physics we think is relevant to late times in 3D, with just about all the physics we can think of put in there. They explode naturally. Most of the models explode without artifice. 3D and multi-D effects are crucial, in particular the turbulent stress of the matter will cause, that stress contributes to the explosion. I can go into detail, but I want to give just the broad overview in this talk. And so we've done about 30 state-of-the-art 3D simulations, which involves about 2,200 model seconds. Now a second may not seem like a long time, but our time steps are microseconds. So we're doing 10 million steps in a simulation that involves 33 million zones. We're doing multi-group radiation transport of multiple neutrino species. So it's expensive. And so the two things that have enabled what I'm going to be showing you are codes that now are efficient and fast And you couldn't always say that when you were talking about 3D. And there's supercomputer resources available that if you're lucky, you can get access to. That combination has allowed us to get this 200 number model seconds when the rest of the world combined is 10. And so what we can do is look at many different models, any one of which would be just sort of a point in theory space, and you didn't know how it connected to anything else. But you do many models, and you start seeing lines, trends. A low mass progenitor at 8 solar masses, a high mass progenitor at 60 solar masses, and everything in between to some degree, not everything possible. And then you start seeing the trends that connect energy of explosion with progenitor structure, with recoil kicks, with the nucleosynthesis, with the mass of the neutron star left behind, with whether a black hole is formed. Now you can do real science. And this problem has been around with us at a reasonable level of theoretical understanding for 60 years. There's more to do, but we have the trends, what lower mass progenitors do, massive stars, higher mass massive stars, etc. And I'm going to try to summarize that. There are caveats. The progenitor models themselves, we inherit. Massive star evolution, people do. They evolve to the point of instability in the interior. People know about the Chandrasekhar mass? Yeah? Maximum mass of a white dwarf. Basic physics, Nobel Prize. Well, the Chandrasekhar mass is not just one mass because there are thermal corrections that are directly connected to the stellar evolution. And those thermal corrections differ from among the progenitors. And so that you have to incorporate. It turns out what that structure is maps directly into the outcome. A problem is that that structure doesn't map so directly, according to what we understand now, to the progenitor mass, because those progenitor mass evolutionary calculations are in process. That theory has not converged. Okay. There are neutrino effects that would still be nice to worry about. Neutrino oscillation effects we know are real. Not the standard neutrino oscillations that explain the transformations in the sun to the detectors underground, but other oscillation effects, so-called fast flavor conversion. It's hard to do. You have to solve the density matrix with off-diagonal terms that have correlations between the neutrinos when the diagonal terms are actually the things you do if you're solving the Boltzmann equation, which you're doing. That was a long sentence. If you understood that, I don't have to say much more. Numerical techniques have improved, but they can always be improved. But the basic mechanism, basically, I think has been resolved. Okay, a few more words. Neutrino-driven turbulence is important. If you do it in 1D, some models explode, but very few, and we understand why. That was a problem for many years. If you do it in 2D or 3D, you allow the turbulence to be generated, and that turbulence is due to the neutrinos that are coming out. They're coursing through at these high densities and temperatures. They're produced in abundance. A fraction of those neutrinos as they get out are depositing their energy. That energy deposition can energize the explosion. However, it's generally not enough. But if you include the turbulent stress and the turbulence that is generated by the neutrinos themselves, you have heating from below. It's boiling water in a stove. And you get bubbles. And those bubbles have a turbulent stress distribution, which is an anisotropic pressure tensor. It comes out of the simulations. And when you add that extra stress to the neutrino heating, almost all the models explode. Sometimes they stall a little bit, then they are energized, and I'll show some of that. One of the other things that's important, and you'll see this, is a simultaneous accretion and explosion. The breaking of spherical symmetry is crucial, so you can't see that in 1D. But when they explode, they can explode more in one direction and still accrete in the other direction. In spherical symmetry, you explode and you generally don't fall back. Well, why would you care? That fallback is accretion luminosity. You're getting the gravitational energy of the infall hitting the surface, generating neutrinos, and keeping the engine going. You can't see that in 1D. In 3D, it happens. That helps. I could say too much. All right. So what I'm going to show are correlations between a lot of the observables, and what some of them are the explosion energy, the neutron star mass, whether you form a black hole, and we don't have the full black hole mass distribution yet because it's complicated. the nucleosynthesis, the production of the elements. When people did these calculations in spherical symmetry, they frequently didn't get explosions, and that was unsatisfying, so they faked it. So all the nucleosynthesis in the literature for the last 50 years is faked. Now, doing it right, quote unquote right, doing it better requires all these tools, and it's complicated. That's the reason people faked it. But what we see is with the nucleosynthesis is fairly different in many respects when you do it in 3D. And we can understand why. The morphology of the blast, as I mentioned, these things are not spheres. You can induce spin. You can start out with an unspinning, a non-spinning object, and that stuff that's falling back can have an impact parameter. An impact parameter, angular momentum. The net impact parameter, net angular momentum. Spin. And so all these models have no initial spin. But all these models end up spinning a little bit. Some a little bit more than others. That's interesting. There's a kick. There's a recoil. You explode more in one direction than the other. Momentum conservation. You get a recoil in the object, the residue left behind. B fields, that's one thing I'm not going to emphasize. We want to get the origin of pulsar magnetic fields and magnetar magnetic fields. People heard of magnetars? Yeah. They're pulsars with high fields. So which objects give this? We have ideas. We don't have any proofs. So that's certainly a goal. And one of the important things is the gravitational wave and neutrino signatures of these events. It's important to theorists, but we can see only the galaxy, more or less. And there's only about one every 50 years, one every 60 years. That's frustrating. But we continue to predict what the gravitational wave and neutrino signatures are, and they're really sweet. And then every one of the objects, you explode, you still have neutrinos coming out, and there's a wind coming off. And so you get a primary explosion, and when the pressures have gone down enough, you get a secondary explosion. Was that part of your conception? 10% of the energy. And a lot of interesting nucleosynthetic effects. Okay. And so stellar revolution, this is on luminosity surface temperature diagram, a theorist HR diagram, and this is just an example of evolution where you go into this direction to low temperatures. You're also going to large radii. That's a red supergiant, a blue supergiant. You can eject the hydrogen and you get a helium core. All these things, massive stars could be in all these states. And when these things explode, what you see depends a lot on what's left. But the mechanism may be exactly the same. So with the same mechanism, you get different manifestations, different supernovae. That makes it a little bit more complicated to connect the observers with the theorists. But it's a goal. Oops. Okay. So this is what I was talking about in the Chandrasekhar core. Each one of those lines is a profile. Here's the central 0.5 solar masses interior, 1 solar mass interior, 1.5, etc. Each one of those lines is one of those profiles at collapse. This is a collection of models that's put together using the Kepler code. And there are all sorts of features here, but I want to call your attention just to two things. Three things. Note this high central densities. This is in CGS. This is 10 to the 9 grams per cubic centimeter, 10 to the 10. This is a very compact white dwarf. But look at that steep declivity there. That is a low compactness object. The density gradient goes really low. And those are generally associated with low mass massive stars. That might be 8, 9 solar masses, 10 solar masses. But then you get these other profiles that are much more shallow. And what I'm going to try to convince you of is that the shallowness of this determines all the outcomes. This is so-called high compactness. This is low compactness, a lot of mass at a given radius. Low compactness. Now, there are some things in the literature that say only these things can explode. This is completely wrong from many different perspectives. So-called low compactness is necessary for explosion. If you've heard that, you've been reading the wrong things, listening to the wrong people. Then there are these other models that are generated, and we've tried to reproduce some of this. Now, this looks qualitatively similar, but if you look in detail, particularly model by model, these are not the same structures. Although qualitatively, they look fairly similar. There's the silicon-oxygen interface. There's a jump there. This is steep, this is shallow, this is steep, this is shallow, etc. But in fact, the mapping between the star, let's say a 15 solar mass star, and its outcome is not known because that 15 solar mass star is calculated differently by different groups around the world. And I have a slide which will really shock you, and I decided not to include it. So that's one of the ambiguities. And so what we've done is to try to map these structures with the outcomes. And then once we have that, once the structures are mapped with the progenitor models, 15, 16, 17, 18 solar mass model, then we can make that connection. Right now it's very provisional. Okay, well this is just a plot. Look at the blue dots. That's the compactness parameter. High means shallow, usually high mass, and low means steep. And you see that it's non-monotonic in a certain range. And people had said that only these things could explode, and these things form black holes, these things form black holes. It's not necessarily true. There's a song that includes that, by the way, if you're old enough to know it. So when we do these calculations, here's the compactness again, 0.2. Don't worry about the actual units. This is low compactness, high compactness, calculated in a certain way. These black dots are the progenitor models we inherited from one group. The blue triangles are models that exploded. The red triangles are models that didn't. And they're all clustered there, and those models would form black holes. It's not the only channel for black hole formation, but it's the quiescent one. But most of the models explode. Okay. So at the top left, you see the average shock radius. A shock wave is produced at that bounce. And the shock frequently slows down and stalls, but not for long. And so each one of these colored models is one of these progenitors, 9, 10, 13, 15, up to 60 here. And we've done a lot more than this. And you can see very easily, anything that goes up like that, 500 kilometers, 100 kilometers, a shock stalls around here, 150 kilometers, but then it's re-energized. And most of the models actually explode. Now, if you've been following this subject over the years, let's say every 5 years you get a dose, you wouldn't have seen this. So the new capabilities have enabled us to see, without artifice, any multitude of explosions. A few of the models don't explode. And I'm not going to go into detail here because that would really get into the weeds. But people can ask questions if they like. And then this is on a larger scale, 5,000 kilometers, and this is how they're blowing up. At 10 to 20,000 kilometer speeds. Here's where you start. It doesn't take long to blow up. Here's a delay. That delay has been a problem for decades. It's now been overcome. This is a general context where that's the stalled shock. This is before explosion. And each one of those trajectories are tracers, Lagrangian tracers of matter elements in the turbulence behind the shock, where the neutrinos are heating and causing the bubbling and the roiling. This just gives you a general context for one particular model. And you see the shock is not perfectly spherical, and the material inside is certainly not. This is just an example. This is an example, a still of the central region. The scale is about 100 kilometers. That's an isodensity surface. And then you're going in. Each one of these tangled threads is a turbulent region. This is convective on the outside. Then it's radiative. There's no convection. Then there's convection on the inside. It's complicated. And this is just a snapshot of a neutron star at birth. You leave behind, most of the time, a neutron star, and it's hot. It's lepton rich. And it's going to deleptonize to become a neutron star over time during diffusive processes. And it's going to shrink. And so anybody who knows about the Kelvin-Helmholtz phase of star formation, this is the Kelvin-Helmholtz phase of neutron star formation. And we followed this for many, many seconds, watching the thing shrink. And I'll get back to that when I talk about gravitational waves. And so you get these complicated turbulent structures. This is just a physical scale. Inner convection, radiative region, outer convection where a lot of the supernova action is. But it's a complicated context. Numerically, there are going to be differences. But physically, every one of these aspects and regions is well motivated physically and in detail. So this is just an example. Note the scale over here, 350 kilometers, 500 kilometers, 2,200 kilometers. Material is falling in. There's the shock wave. And this is just a stop. You can see all these bubbles. They're colored by entropy. And that's what I mean by the roiling and boiling of the material behind there. Notice that the scale has changed. You move back. Stuff is falling in. Blast is moving out. There's a lot of action. Okay. Now, we've done many models, as I said. I just want to bring you through a few of them, the general structures. This is our most spherical model. The shock waves are always more spherical, although they're not completely spherical, than the matter distribution. And this is an iso-nickel distribution. Nickel 56 is produced explosively. And you can see the distribution is reflected in the distribution of the nickel. The distribution of the entropy and the roiling and boiling is. Now, that inner region is actually falling in. So you get the simultaneous accretion and explosion, which is supportive of the explosion itself, which you don't see in 1D. And so this is just another still. There's the shock wave, but this is very asymmetrical. Stuff is still falling in here, but the blast wave is still moving out. That's where the neutron star is. You can see how off-center this one is. Blast wave. This is a 10 to the 51 erg explosion. Very asymmetrical. And this is just a couple of stills of different models going up in mass. And that's the morphology we're getting. And we can't predict ahead of time what the morphology is going to be. It's chaotic. It's turbulent. We don't know what the distribution function of the various parameters, if you calculate a dipole or a quadrupole of the mass distribution, are. That would be something for future work, but it's still a complicated thing. And I'm not going to say we understand it that in such detail, because it's chaotic. Okay. Now, I'll note there's a 60 solar mass model here, and most people would say, well, that massive a thing has to be a black hole left behind a neutron star. It's more complicated than that. Now, let's see if I can actually get this thing to work. No. Okay. Now, I couldn't resist, so we've put music on this one. We have options. This is the classical variant. And we have a techno version. And this looks like what you saw before a little bit, but it makes an important point. Here's that isodensity surface and all that turbulence in the inside. All that stuff is falling in. There's that protoneutron star. And that's going to be shrinking gradually, although not in this movie. But at the same time as it's, well, shrinking gradually. At the same time as this is formed, that's the neutron star at birth. The blast wave is coursing out through the rest of the star. And you notice stuff is falling in right there? And there's a wasp waist pinch, simultaneous accretion and explosion. And it's not a sphere. Okay. So I want to show correlations that we've seen. It's not the final word, but it is a useful word between the supernova energy, the nucleosynthesis, what's called alpha-rich freeze-out, which is a version of nucleosynthesis the cognoscenti would know about, kicks, debris morphologies, and all these other things, which I mentioned before. This is the baryon mass of the object left behind versus time, log of the time. So this is 10 milliseconds, 100 milliseconds, 1 second, 10 seconds, 100 seconds. And each one of these is a single model. And so you see this particular model, which was a low mass progenitor at a low compactness, very steep density profile, figured out what its mass was going to be early and it was going to be low. And when you make this a gravitational mass, it's about 1.2 solar masses. And then as you get less compact, you have more accretion. The final neutron star mass is larger. These stars are when the thing exploded. And you want to see it flatten out. Flatten out. The dashed, or dotted or what, curves all form black holes. These things are still accreting. And that's an interesting story in and of itself. But if you remember those shock profiles, those radius of the shock profile, most of them were going up, but a couple were going down. And that was those two. But these are also black hole formers. The explosion started there, there, and there. The black hole formed there, there, and there. The time between the explosion and the black hole formation was so short for this one because it accreted so fast, it had no energy to overcome the outer envelope binding energy. And it fizzled. And this is forming a 37 solar mass black hole because it started with 100 solar mass ejected material and it fizzled. This one had 1.5 seconds of neutrino driving, and there was fallback, but it got up to about 3.5 solar masses and it's flattened out. We formed a 3.5 solar mass black hole in the so-called low mass gap with an energy of the explosion of 1.6 times 10 to the 51 ergs. 10 to the 51 ergs is a so-called beta for Hans Bethe, because he was very interested in supernovae. That's energetic. This one is even more energetic. It's 2.5 betas form the black hole, and we've continued this further. This is an old slide, and it ends up at about 2.6 solar masses. A black hole of 2.6 solar masses in the context of a vigorous supernova explosion. That is heresy. Okay? But we have all these models. In the past, people would have had one model and they would have gone to here. They wouldn't have continued it further. Again, this is a log. We've gotten most of these models out to way over here. And when the black hole forms, our code crashes, unfortunately. And so we can put a point mass in there and we can continue the accretion. And then we've done that. And this one has been carried out to 21 seconds and we're carrying out further. This one's being carried out to 100 seconds. Okay, you notice this one? That doesn't look like it's going up. This one exploded with a low energy. And at the end of our calculations using the code Fornax, which is the one we're using for this purpose, we designed from scratch to do these problems. We thought that that was just a nice supernova, but then we mapped it into a larger code and watched the development, and after 1,000 seconds, it had accreted another 4 solar masses. It had enough energy to explode, but the mass cut was further out, and that fallback made it a black hole. But it was a normal supernova, and in fact it ejected nickel. The nickel was produced deep inside, but the nickel became bullets and went ahead of everything else before the stuff fell back. And so it produced 0.08 solar masses of nickel and it ejected 0.03. 0.03 solar masses of nickel, half a beta. There's no observer that would have been able to distinguish that from a regular supernova. But it left a black hole. And that's not in people's minds. It may not have been in yours in the beginning of my talk. And then we just have correlations of various sorts. And there are too many of these, so I'm going to emphasize only a few. First, compactness, remember that. Low compactness, high compactness. The neutron star gravitational mass left behind is almost monotonic. That's a prediction. People have never seen this before because they've done one model to short times. They've never seen the asymptotic behavior, except for the really lowest mass ones. Now, for a whole range of these things, we can asymptote to the final mass, and that's what we see. This is an important slide. This is the total explosion energy versus time. And when these things explode, usually in this phase here, when you add up all the energies, they're negative. Negative energies don't give you positive kinetic energies at infinity. There's energy conservation, and it doesn't work. You have to keep depositing the neutrino energy over many seconds in order to see it flatten out, in order to see it asymptote. Almost nobody had calculated it further. And when they quoted explosion energies, they ignored the binding energy of the envelope they had to overcome. They called it the diagnostic energy. If you give it a name, people will believe you. But it was wrong. And so you have to do these calculations to much later times. Negative energies at explosion. This is explosion energy versus compactness, quasi-monotonic. These are black hole formers, but exploded pretty vigorously. Explosion energy versus the time of explosion, a little bit messier. But if you explode earlier, it's because your accretion rate isn't so large. You need that accretion to deposit neutrino energy. You need the luminosity. So if you explode early, you get a low energy explosion. You explode late, you get a high energy explosion. It's completely opposite to what astrophysicists thought 10 years ago. Explode early, well, you have more time. It'll deposit energy longer. It's not the way it works. Neutron star mass left behind, 1.3, 1.4, 1.5. The average neutron star mass left behind is something like 1.4, 1.5 solar masses. Versus explosion energy. There's a correlation. This is calculated, and this is the end of the calculation. Calculated, and this is the end of the calculation. We kept evolving this plot. This is interesting. The explosion energy versus the binding energy of the envelope. The more bound the outer envelope, the larger the explosion energy, because the more bound, the higher the compactness, the larger the accretion rate, the larger the luminosity, you get the larger explosion energies. And if people have looked at standard models of stellar winds, the velocity asymptotically for a wind is the escape velocity from the surface of the star, deep down. There's a correlation there, and it's not coincidental. And the asymmetries, the more energetic, the more asymmetric, with a lot of noise. There are a lot of myths in this field, but I'm going to be nice. Now, one of the things is that, as I mentioned, there are winds that come off. And these winds aren't spherical. The old Parker wind, people remember Eugene Parker? Parker Solar Probe, pioneer in plasma astrophysics. He had a model for the winds coming off of stars. And for the sun, it was electron conduction, heating stuff. And when he did the calculations, hydrostatic equilibrium, it turned out that you couldn't get hydrostatic equilibrium for a certain profile of temperature exterior to the object. If it was steeper than temperature going as 1 over R, then it was unstable. But you had to have a finite pressure at infinity to put it in hydrostatic equilibrium. You don't have a finite pressure at infinity. And so he naturally thought it was the wind. And you got those shallow profiles with electron conduction, because electron conduction is very temperature sensitive. And when you put the numbers together, you get 1 over R to the 2/7, which is shallower than 1 over R. In the neutrino case, if you put the numbers together, you get 1 over R cubed root. That's more shallow than 1 over R. It naturally wants to form winds. It just wasn't able to because the pressures were so large. But when the pressures go down after the thing has exploded, it goes unstable to a wind. Okay, and so this is just an example. Here's a low mass progenitor, 9 solar masses. These are mass contours. 1.35 solar masses, 1.349 solar masses, 1.348 solar masses. And look what they do. Here's 10 kilometers, 100 kilometers. These things settle onto the protoneutron star, and then they bounce off. They're not bouncing, they're being ejected in a wind at later times. This is one of the more exotic ones. This is the shock wave. The color is speed. And look at that inner structure. And look at that number. This is stuff moving at 45,000 kilometers a second. The shock is moving at 20,000 kilometers a second. The faster stuff is the wind coming off the interior. And it hits that inner ejecta, contributes energy, is decelerated, but you wouldn't have seen this if you didn't calculate to late times. Now you could think theoretically that something like this should emerge, but it was too many steps, right, for people to really, but we can see this in the simulations, and every model does this. We're not making this up. Well, I hope we're not making this up. Nucleosynthesis, the electron fraction, which is the number of electrons per protons plus neutrons, right? For oxygen 16, it's 0.5. For hydrogen, it's 1, ignoring deuterium, right? So normal stuff is 0.5 except hydrogen. Well, here's 0.5. And this is the electron fraction distribution of the ejecta. And you can see, this is log. You can see it's mostly 0.5 stuff. It's mostly oxygen, carbon. But look at the tails. It's mostly proton-rich. And so you get completely different nucleosynthesis because of this. And you don't see this if you don't do the simulations with all those blobs, because they don't have the same electron fractions. There's also stuff that's neutron-rich. This stuff can give the first peak of the R process. People know about the R process? The origin of uranium and thorium and europium and platinum and things like this. And there are peaks in the R process. There's the first peak. There's a pygmy peak. There's a second peak. There's transuranics. We don't think that supernovae are a source of the R process, but some of the neutron-rich models produce the first peak. I'll get back to that. But this is also important. Nickel-56 is a radioactive species. It powers a lot of the light curve of many supernovae, particularly those that have lost their hydrogen envelopes. And we see the production of this, and we have to calculate for late times. The smaller models, and again, these are colored by compactness. The smaller models, are they? No, they're not. Ooh. But these are the lower compactness ones. Asymptote pretty quickly and have low nickel yields. And that's what we said before, low compactness, low nickel yields. And you go up, but look, it takes seconds to flatten out. And some of these really haven't flattened out. And you can produce a whole range of nickel yields, and it's very important for the observations of supernovae. And this is the nickel yields versus the zero age main sequence. This is 10 solar 20 solar 30 solar. There's a lot of noise in here, but generally it goes up like this. But versus compactness, it's much more behaved, although there's a little bit of noise here too. That's complicated. But there are trends. Explosion energy versus nickel, almost perfect. That's a prediction. They're both observables. There's some inferences for supernovae that are all over the map here. I don't know how systematic these problems are, but we just show our models do this. And hopefully these things will comport much better in the future when the observations get better and more credible and the theory improves. But it's not up here. It's not down there. And we didn't force it to do this. It just came out. In Cassiopeia A, the supernova remnant that emerged 350 years ago, modulo light travel time, has an iron distribution here, which I showed you before. There's an iron right there. This is radioactive titanium-44. And they're not the same distribution. Well, in the past, what people had done is they had calculated it here and said, this is how much titanium is produced, and it's not consistent with what we see in the collection of elements in the final state. And so there's a problem. There's been a problem for 20 years. And the problem was, and we just published this in the Astrophysical Journal, you didn't calculate long enough, and the channel for the titanium-44 production was not the channel they thought. Titanium-44, if you look at it closely, it's an alpha nucleus. You take the alpha particle, you multiply by n. N is an integer. Okay, that gives you the 44. Nickel-56 is an alpha nucleus. Alpha particles are alpha nuclei. Oxygen is an alpha nucleus. Carbon's an alpha nucleus. When the blast wave goes out through that carbon-oxygen zone, it'll produce mostly alpha nuclei by explosive nucleosynthesis. People thought that titanium being an alpha nucleus and nickel-56 being an alpha nucleus, that's where both would form. And that's true to some degree, but only a third of the titanium produced is actually produced coextensively with the nickel. It turns out that if you didn't do the calculations in 3D, following all those trajectories, all those tracers, and doing the nucleosynthesis and all these things, some of these things went out, came back, swirled around, etc. You can imagine the net nucleosynthesis of that is not quite what you would get if you did a calculation in spherical symmetry. And you also open up certain channels for titanium production that you don't have for nickel. The net effect is the titanium production just went up, but you had to do the calculations for 10 seconds. And remember, most people stopped here. So doing the things in 3D to late times not only gives you the systematics and gives you the full panoply across the continuum of progenitors, but it also solves various problems that have been bedeviling people that didn't know would be solved by doing long-term 3D simulations, which are now available. And more nucleosynthesis. There's too many details here. This 0 would be solar distributions, and you see some excesses here. We haven't done the weightings or anything like that, but the point here is that you can produce some interesting heavy element distributions depending on that electron fraction. And what the weighting is not so clear. And this is the same sort of thing. Here is the first peak of the R process, this zirconium-90 here. A couple of models that have a lot of neutron-rich ejecta will give you that peak. But there's nothing beyond that in these models. Many models don't do that, though. And these are just examples. The difference is orders of magnitude. And it's very sensitive to that electron fraction, which you cannot get right in 1D. Okay, let's see if I can give you. And this is just movies. So there's the 17 that was very asymmetrical. You see stuff is falling in. You can actually see it falling in. I'll do that again. Stuff falling in. But it's still blowing up. Ah. And this just gives you each one of these trajectories. For one reason, I always have trouble with this one. They're not, each one of these trajectories is a nickel bullet. And we did 320,000 of these, but we didn't do this in the movie. To show you the spray that comes out. Again, this movie may not work. Yeah. All right. And that just gives you another example. The colors are actually, the purple is going to be nickel, and the blue and the yellow are nickel. And you can follow each trajectory. When we put these on Zenodo, you have 320,000 trajectories for 20 models with all the nucleosynthesis, and you can calculate your own nucleosynthesis if you want. This is our most spherical model, and you see some of the blobs are small. A lot of the blobs are small. Shock is pretty circular. That's because it exploded so soon that the turbulence didn't have a chance to develop much. It didn't need it much. And this is an example of the nucleosynthesis. This is a little bit more spherical than most. Now this is that 17 solar mass one. I just want to call your attention. This is a scale, this is 427 seconds. So we took the model and we mapped it into a code that followed the hydro after all the nucleosynthesis and all the energy was deposited. And it blasted out through the outer oxygen shell. The outer oxygen shell is this teal, and the nickel is this magenta brown. And you see it blasted a hole through the oxygen. This is a prediction. The nickel is produced deep inside, but in the final state, the nickel can be outside stuff it was originally inside. This is carrying out the calculations, one example calculation, much later. That's the surface of the star. Look at the time. This is hours now. You have all these instabilities. There's a reverse shock went into the interior. It expanded. This is our most spherical model. There's a lot of asphericity here. So looking at the morphology, you have to do the propagation of the blast all the way to many, many, many hours. And there are a lot of hydrodynamic phenomena that are encountered along the way. We're in the process of doing this, led by David Vartanian. Okay. As I mentioned, one of the things that we see are the recoil kicks. Here are examples. Again, the theme is, if you stopped here, you don't see what these kicks are. 500 kilometers per second, 1,000 kilometers per second. Here, a few hundred kilometers per second, it flattens out. Others take a much longer time to flatten out. Some haven't flattened out at all. They're going to flatten up here. That's 2,000 kilometers a second. Most of the models are down here. They're a few hundred kilometers a second. And pulsars are the fastest, one of the fastest populations in the galaxy. Not the fastest, but one of the fastest. They have average speeds in the galaxy of about 300, 400 kilometers a second. It's probably produced by this. Just recoil, because of the asymmetry in the explosion, which is a multi-D effect. However, the systematics that we see is a mess. The lowest mass progenitors, and this is gravitational mass here, and I don't know why we spelled it like this. We were too enthusiastic. But the lowest mass ones from the lowest mass progenitors generally gives lower kicks. The higher mass ones, all over the map. But the range is typical, but we haven't converged on this. We don't know what the scatter is. We think it's just chaoticity. But we haven't demonstrated that, because there are systematic directions of things, and we have to work that. But that's, each one of these models, again, in the past, you could do a three-dimensional model in a year and make a mistake. Now we can make a mistake in a week and do 20 of them. So the important thing in science is to be able to make mistakes quickly, right? That's what the tech bros tell you. Okay. Unfortunately, they're not always wrong. Okay. The anisotropy, of course, is directly connected to the kick. There's also a neutrino kick. There's an anisotropic neutrino kick. It's usually subdominant. For some models, it can dominate, but only at the lower kicks. That's an interesting story. What's this? And there's a rough correlation. This is not a great correlation, but you get something. Higher explosion energies, higher kicks. You would expect something like that. Higher explosion energies, you get higher velocities, you get more mass. And so more mass, more velocity, more impulse. But you have to have the anisotropy, and so there's a lot of mess. Let's see, no. As I mentioned earlier, that there's induced spin. Now these models were started without any spin, but the things left behind were spinning. Most of the spins aren't too large, but there is a systematic behavior. And this is just examples of what we saw. And it's messy, so I don't believe in detail these numbers. I'm trying to look for the systematics, but you don't know what the final results are until you calculate it for a long time. These models have been carried out to about here now. Some of them asymptoted pretty early, but these calculations are not generally done until to the point it's necessary. There's an interesting correlation that is, the referee said we couldn't mention in the paper. What we see is an angular momentum direction and a kick direction, a dot product. These are the unit vectors that sort of cluster up anti-parallel and parallel. But the fact that there's a gap in here is not too significant. We haven't done enough models. But it's suggestive that we might have a correlation between the spin and the kick due to this process. The problem is we know it can't be the whole story because these things are rotating. And some of them are rotating pretty fast. The crab is rotating now at 30 hertz. It started out at 15 millisecond period, half as much, twice the speed. Now that doesn't have a lot of kinetic energy. It has 10 to the 50 ergs. Not 10 to the 51. But it's interesting. But that's faster generally than we would think the crab would have been, because the crab is supposed to come from a low mass star. And we get low induced spins for low mass stars. So that does not explain the crab. It's just an interesting physical effect that in the end might explain some of the distributions of the spins of neutron stars at birth. Work in progress. And the neutrinos also give a kick, but look at the scale. 40 kilometers a second, 20. It can vary all over. And we've looked at this in great detail in a paper here. And this is the spin. I'm not going to dwell on that. So what we also find are black hole formation channels. Now, what I'm going to show you is part of a paper that's basically finished, except we had to redo some calculations to much later times to see what the real fallback was. But the standard black hole formation picture is that it's a failed supernova. So the shock is there, but it doesn't blow up. And the material keeps accreting until it goes above the maximum mass, and then it accretes more and more and more, and you gobble up the whole star without a display. Well, that probably happens, something like that, although there's always going to be a display. You're not going to accrete something the size of Jupiter's orbit into such a small volume, completely spherically. It's turbulent, so stuff is accreted and it goes off to the side here, off to the side here. You're going to get centrifugal barriers of all sorts. It'll be rotating. There's no way that something that big, when you collapse it, no matter what the angular momentum is, as long as it's not 0 to the universe's machine precision, that you're not going to form a disk. And with disks around black holes, you get jets. How energetic, you don't know. It's hard. We find 4 black hole formation channels, not 1. And I'm not going to show them all. You'll have to read the paper when it comes out in a couple of weeks. But I will show one in particular. And so we break it up into different channels. We see that black holes are formed over here, which is a really bad place. Just, whoops. All right. Yeah. That happens. It forms where that says black hole channel 1. Now, we think that we get black holes in that region, and that was the region where the shock went up like this, went down, and then it just kept going. That was a failure. But we didn't see many of them. But we get them in this intermediate compactness region, which the observers say, that was half the supernova. What are you telling us? And we, of course, think it's the other guy. It's the stellar evolution models. We don't know that's true. But there is a channel where it's hard to explode. This is really easy to explode. Remember the declivity here of the low compactness. This is really easy to explode. By the way, some people thought this was impossible. You have to get these to explode to get 10 to the 51 ergs. They were completely wrong, and they screwed up the field for 10 years. 8 years. In the intermediate region here, we have trouble exploding for a variety of reasons. Now, it could be the progenitors. It could be that we need higher resolution. When we do higher resolution calculations, lo and behold, we find that things explode more easily. That's good. The other direction would be bad, because nature is infinite resolution, as far as we know. Another black hole formation channel is BH channel 2. Look at how high the compactness is. Just look at that curve. Everybody thought that would form a black hole. Fine, but it had to be quiet. This one is not quiet, and that's what I want to show you. That one is the one in the circle at the top right. The helium core mass is really large. The compactness is the largest in that whole set of solar metallicity models we got using from the Kepler code. But it's a blue triangle, not a red triangle. And I showed you this before. Well, this is back of the density profiles, but now we've superposed, we've done it in compactness. You see the blue drops and the orange shallows. Look at that red one. That red one was so shallow, the accretion rate was so large, when it exploded, it almost immediately formed a black hole and it aborted the explosion. That was the 100 solar mass model. But there are also those models just below them. And both of those dashed curves, those orange dash curves, let's see if this one, no, I guess, I hate using this. This doesn't work either. Okay, just follow my finger. Okay, those explode nicely. I'll show you one example. But this is just the same sort of thing. Mean shock radius on the left-hand side versus time. And you get the low compactness easily exploded, and then delay, and then it explodes. And you can see where black holes are forming. Every one of those curves explodes nicely, but leaves behind a black hole. Okay. The bottom right is the so-called lapse. It's a general relativistic lapse. It's basically the redshift from the center. It just gives you the degree of relativity. And when that gets really relativistic, it actually forms a black hole. And we see that happen. As I said, when it forms a black hole, our code crashes. And then we have to map it into something else. But you can see how on the bottom right, you can see how the lapse changes from 0.8 to 0.35. So the code is following a huge range in relativity. Okay. So this is the 40 solar mass model. And you can see the shock settles down, then it starts to wobble. That's a spiral standing accretion shock instability. Look at the accretion on the bottom left. That's huge. And again, it's accreting it with impact parameters that aren't zero. So it's spinning up that central region. The red stuff is high entropy. The stuff is exploding, but it's accreting from this bottom part here in that direction. But look at those jets. An oblate object is rotating so fast that only the poles are hot was formed. We rotate the camera, a black hole forms. But it formed at such a time that shock wave had already gotten out pretty far. Look at how far that is. The driving turned off. That's why you don't see that jet continuing with that yellow and green stuff. There's nothing coming out anymore. But it had enough energy deposited that in fact it exploded. Now, when the black hole forms is a function of the nuclear equation of state, what the maximum mass of a neutron star is. And we're using a certain nuclear equation of state. So the timing is going to be different for different equations of state. We're suggesting a qualitative thing, that when we really know the nuclear equation of state, that we will have converged to understand the numbers. But qualitatively, this type of thing explodes asymmetrically, gives kicks, very high energy explosion, and left behind a 3.5 solar mass black hole. I want to end with a gravitational radiation. I could have mentioned the neutrinos, which are near and dear to my heart. But then I'd be going over too much. The gravitational, you have a gravitational wave signature because it's not spherical. You have a time-changing quadrupole moment. Stuff is moving fast, a lot of mass, fast, a lot of mass, gravitational waves if it's asymmetrical. Well, you saw the asymmetry. So you just calculate what the time-changing quadrupole moments are. We have the full quadrupole tensor. You get gravitational radiation in different directions. You get two polarities, polarizations. And so we calculate all that. And I'm not going to show a lot, but I want to give you the essence. If you look in the top left, those are different times. So the bottom one goes out to 5 seconds. The top one goes out to 1.75 seconds. Those are just different models. And that blue curve, so we show two polarizations there, but don't worry, blue and black. Just look at the blue. It doesn't last for very long. There's 1 second. It's very stochastic. You can't template that, right? LIGO likes templatable things. They've pretended over the years that a supernova is templatable with a sine Gaussian distribution. It's because it's analytic. Okay. Look on the top right. The top right is what you see when you take a spectrogram, frequency versus time. And that has structure. Look at that line. That line is a fundamental mode of the oscillation of a protoneutron star. It's being excited astroseismologically by the stuff that's falling back, hitting the surface and causing the object to ring at characteristic frequencies. We're doing astroseismology. Just like people look at stars and see pulsations, they have P modes and F modes and G modes. That's an F mode. And in fact, for the quantum mechanics in the audience, there's a G mode and an F mode, and they have the same quantum numbers and they mix. And you get avoided crossing, just like in quantum mechanics, just like in neutrino oscillations, because of the coupling between the modes. And that's what that dark region in there was. I'm sorry I don't have my pointer, but I gassed it up before I came here, but evidently there wasn't enough gas. But look at the trajectory. That frequency is increasing inexorably because the protoneutron star is shrinking. The frequency is changing. Can you imagine what you could learn if you could see that frequency evolution? That frequency evolution is directly connected to the neutrino losses. So you get neutrino data, you get gravitational wave data, Stockholm. Well, for somebody. That's amazing. And every model does that. So look at the bottom. The bottom is one of those curves. Then you sonify it. The frequency goes up, right? Every one of them does that. And I couldn't resist doing another one. It looks all stochastic, but the underlying structure is there. That's what you want to look for. The other thing you see is that zero is zero strain. That's the strain, gravitational strain. It's actually connected to strain times distance. So it's in centimeters. But it doesn't come back to zero. That's called gravitational, that's called memory. It's like Christodoulou memory. When you have merging black holes, there's a kick to the black hole, but there's also gravitational waves off the gravitational waves. And it leaves behind a non-zero displacement in the metric. And we see this with almost every model. When a black hole forms and there's no explosion, we don't get the memory. We get a little bit of memory from the anisotropic neutrinos, but you're not exploding. So the thing gets back to where it was. But when you explode asymmetrically, your metric isn't going to go back, which is fascinating, but it's a low frequency component. And there's systematics with compactness, of course. And this is black hole formation on the left. They both explode. And on the right, it didn't explode and just kept going. Messy, 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 interesting time structure. There's time structure in the gravitational waves that correlates directly with the neutrino time structure. Interesting. And you get how much energy is radiated. It's not a lot. But this is the sort of curious thing. Look at look at the numbers. It's 10 centimeters, 20 centimeters. Those are big numbers in this game. That's the matter component. The neutrino component, 1,000 centimeters. The mass energy of the neutrinos irradiated aspherically doesn't give you a lot of energy. It's all at low frequencies, But the strain is huge. It's out of the LIGO band because that comes from the evolution of the neutrinos, which is much longer time scale. So you Fourier analyze it, it's going to be in the 10 hertz, 1 hertz, 10th of hertz regions. So LIGO can't see it. But, oh, do I only have a LIGO? When you figure out what the ranges are just for simple detection in advanced LIGO, look at the right column, you can see out the entire galaxy. What I'm not showing you is the Cosmic Explorer of the Einstein telescope, the 3G proposals for the next generation of gravitational wave detectors. Cosmic Explorer will have sensitivity at low enough frequencies that it can see out to megaparsecs. I was once offered $50,000 by my NSF contract monitor, you're not supposed to know this, that if I could prove that gravitational radiation from a supernova could be seen out to Virgo, he'd give it to me, right? I couldn't do it. I just couldn't do it. I tried. Well, maybe we're getting close. Okay, so I want to end with just a summary. There's a lot of new here, and I hope you got the sense that the field has evolved quite significantly. We get explosions without putting them in by hand. The turbulence is important to the mechanism, is important to the nucleosynthesis, to the kicks, of course. We get correlations that can be tested. And most of the models explode, again, without artifice. And this is because we've been able to over the years, put in a fair amount of physics. And I will argue that maybe even some chemistry, so we really do cover just about all of science. There's biology, too. Have you seen some of these pictures? They look really biological. And we have access to supercomputer time of significance to look at the whole field synoptically and not look at theory through a straw. Now, the future is going to be more detailed. There's lots of things we need to understand. I don't think we have everything down quantitatively, but qualitatively, I think the problem is solved. And it's been around for decades. Thank you very much for your attention.
Thanks, Scott. Questions? Let me ask one.
Hey, thank you for this really great talk. I have a lot of questions, but I'll ask one. What physics that's in these simulations is the least understood?
Neutrino oscillations, which isn't in these simulations. The fast flavor conversions that have been invoked, we don't know how to handle those very well. There's a whole subculture that is working on this, but they think as particle physicists. So they think in terms of the solution to the Schrodinger equation, these sorts of things. We have 10 to the 58 neutrinos. When you start thinking in terms of density matrices, then you can start actually, and with off-diagonal terms, you can start formulating in a way that we could actually simulate. But it's a lot more calculation. And unfortunately, those flavor conversions depend on angle correlations. So we have to do multi-angle. And what I didn't say here is we're doing moment hierarchy. So we have the Boltzmann equation, and we take the 0th moment, and we solve the 0th moment, we solve the 1st moment, but the 2nd and 3rd moments we use as closures for the other equations because we can't continue the hierarchy, and we can't do multi-angle because it's too expensive. It will be available. I don't think it makes a huge difference. I'm much more worried about the neutrino oscillations. And we'll see. Now, my prejudice, of course, is that we've understood the systematics, and this is just going to be a correction, but I haven't demonstrated that. There are 3 different techniques that people have developed that might be incorporatable into the calculations we're doing. We're going to implement 2 of them. One of them by Lucas Johns, and another one by Sherwood Richards. And we'll see if we can, what we'll come up with. And we're set up to do spherical models with the fast flavor conversions. And in the next months, we'll have answers in that context. And then we're doing a branch out.
Yeah, first of all, I apologize for being late. I had a class.
It's quite all right.
These things look like bomb codes,
Yeah.
bomb simulations.
Yeah.
And I have to tell you, I've seen many of those.
And you don't believe them.
That I knew were wrong.
Yeah.
Okay? Now, You got the kitchen.
The problem is they knew they were wrong too. Yet you saw them.
Wait a minute, that's a different conversation.
Yeah, I know.
I'm asking the tough question here.
Yeah.
You've got the kitchen sink in these codes. Why should I believe you? What is there anything? Is there what? How many? You know, when I make a theory, I've got to constrain it by experiment, and I don't see an awful lot of experimental constraints here.
Yeah, no, you're absolutely right. The complexity of the problem has distanced us from the observers and the astronomical community to a degree that is unhealthy. You really want to validate what you're doing with observations. That's the proof of the pudding. And we're only now at the cusp of being able to do that. Those correlations were an attempt, because those correlations between nickel mass, anisotropy, explosion energy, these sorts of things are directly testable in certain contexts, particularly nickel mass and explosion energy. The asymmetries, you can measure polarizations of the interior material. All these sorts of things can emerge. But you're right. The major problem is that a lot of this action is in the center, and you don't see it until later. For the morphology, there's a lot of changes in the distribution, so you really have to look deep in the belly. And there's stochasticity. So it's turbulent. So I'm not going to say that every model is correct, and that's why I emphasize sort of the general trends, because these were not available in the past. So skepticism is important. Your skepticism is justified. It's just that this is I think, transformative for the field, because we've been in the dark so long. So these simulations, as you point out, are just like bomb codes, except they have more computer time. And they have a lot of microphysics that isn't available. It can be very complicated. They also have validation protocols. They can actually compare to things. And you're quite right. They frequently have fudge factors. Over the years, okay. They have fudge factors in the codes that try to fit the experiments. And then they don't change the fudge factors for other tests. Anyway, it's a difficult thing. So you're right. I think this is an evolving dialogue with observation, and then that's the proof of the pudding.
Actually, I just had a very related point I wanted to make. So you had that table with LIGO, with gravitation. Yeah, right. And I went too fast, and I don't. So if I have to say, okay, so in the next 10 years of advanced LIGO, I don't know how long advanced LIGO will run. How many do you predict? That's this is a...
No. When embarrassing questions are asked, you want them to be in pairs, okay? And this is an example. There aren't a lot of supernovae per our galaxy per year.
Oh, those are all galactic.
Those are galactic. Look at those are kiloparsecs.
Yeah,
They're kiloparsecs. I'm sorry.
Right.
Yeah, I swept that under the rug. Yeah.
Yeah. Okay. Right.
However, if you can, there's DESIGO, which is a Japanese initiative to measure at a Hertz level or a tenth of a Hertz level, which may or may not ever get funded. There's also Tianjin and Taiji, the Chinese initiative, which would be at lower frequencies between LISA and LIGO. And they would be exquisitely sensitive to this. There's a lot more here, and the low frequency stuff has a lot more strain, as I mentioned, and allows you to go out fairly far. But what I'm not telling you is this is just detection. This isn't characterization. And you want to characterize what you're seeing. And so this is a storied subject without any real data. Because people have been working on this for a long time in isolation in a theoretical vacuum. In a vacuum of theory.
All right. I want to see what to take away from this. We read in the textbook that the low mass progenitor produce neutron star, and it could divide, you go higher mass, you produce black hole.
Yeah.
But it looks like your models say, for some
we have no
high mass to produce certain kind of neutron star.
Yeah.
There wants to be
Yeah.
a case, and then even low mass produced a black hole. So is that
The low mass black hole connection is not so clear in my mind. What we have is there's a certain region of compactness space that's hard to explode. I don't know that they can't explode, so I'm keeping an open mind. But if those explode, every black hole formation scenario tries to explode, and some of them do. And it's not the case that above a certain mass, you form black holes, and below a certain mass, it's neutron stars. The case is above a certain mass, you have more likely a chance to form a black hole, but through channels that you may not have anticipated. And below a certain mass, you're more likely to form neutron stars. I'll stick with that one. But it's not obvious, and it's not what people say in the literature with the simple prescriptions that people use for population synthesis, for example. Those are poorly motivated.
By the impression I got. The other question I have, you mentioned pulsars and magnetars, and all your simulations are hydrodynamic.
Yes, yeah, we were putting in magnetic fields.
What are the possibilities of MHD, so you know what are the magnetic fields?
Yeah, no. There has been work with magnetic fields. We just haven't done it in this study. I did some stuff in 2007, but it was interesting and suggestive. There was work recently by Obergallinger and Alloy, Kotaki, Bernhard Muller in Australia that is trying to see what the magnetic field effects are. Generally, they're subdominant, mostly positive, which is interesting. But they don't know how to really get dynamo action because dynamos require reconnection on small scales they can't resolve. So they have to have a code that will handle the subgrid behavior adequately, and nobody really does. And so this is really an issue. If that is resolved, then you'll be able to say which models give. I will predict here, and because I haven't done the calculation, that more massive neutron stars will form magnetars because of what we're seeing in some of the stuff we haven't published. Sorry.
Two more questions, because
but you didn't hear it here.
Side of the audits, Evan.
Okay, so you hinted at this idea where as technologically we've been able to improve the resolution, the time step, the spatial resolution simulations, we've seen more explosions resulting. So have you been able to explore the numerical systematics?
Mm-hmm.
Have the results, how flat
Yeah.
your results from the resolution of the simulation?
No. It's expensive. Despite the fact that I was saying we were doing all these calculations, wow. To do that type of parameter study in a systematic way is we have to craft it really well. And we're focusing on what we can do that will have the most impact right now. But yes, we did one paper on resolution dependence. Low resolution, really low resolution, didn't explode. Our default resolution exploded nicely. We doubled the resolution in the angular directions above that, and it exploded earlier and more energetically, but not by a lot. And we understood why, because the turbulence was better resolved, and so the Kolmogorov spectrum wasn't truncated. You had more stress at the larger wave numbers, and so we could see the Kolmogorov coming on. If people know what I'm talking about, standard turbulence, and we could see the cutoff, which was numerical. We can't resolve the full inertial range yet. That's going to be interesting. One of the curious things is there's regions in there where the neutrinos are the major viscosity. And we have the velocity dependence of neutrinos with neutrino transfer, so the radiative transfer already has the momentum transfer associated with shear viscosity. The bulk viscosity is already handled because that's a local thing having to do with non-equilibrium. And that's all automatically included. So we can actually simulate with viscosity. And because the neutrinos dominate in a certain region, at large distances, no, at small distances, no. But in an intermediate region, we might be able to resolve the full inertial range, which is never done in astrophysics. But something for the future.
Okay, one more question.
Because the Reynolds number is only 1,000, sorry. For the neutrinos.
Are potential source of our process nucleosynthesis.
I didn't hear the first words, I'm sorry.
Collapsars.
Collapsars,
Could
yes.
be source of our process nucleosynthesis.
Yeah.
And you do blow up several tens of solar mass stars, but none of your explosions result in an electron fraction of 0.2 or something.
That's right.
Required for our process.
That's right. We haven't done it with the magnetic fields. That's the one.
What's going on?
What?
Why do you not see such low?
Because it's just not energetic enough to give you rapid enough expansion. You get the low YEs, because what's happening is you have really neutron-rich stuff, and then it's ejected. If you eject it slowly, the neutrinos are being absorbed on that stuff as it's going out. The neutrinos will raise the electron fraction. That's the super loud charge current reaction, right? That's the Cohen-Reines reaction. So super loud, okay, or the inverse. Related. Same matrix elements. The anti-electron neutrinos are doing the opposite. They're absorbed too. And they're lowering the electron fraction. And so as that stuff is ejected, if it's ejected slowly, then whichever dominates will determine the final electron fraction. It's the electron neutrinos that dominate. So the electron neutrinos will take something that's really neutron rich and it will just push it up if it's slowly ejected. And slowly is a quantitative question, but some are slowly in this context ejected. And so that's what pushes it up to proton richness. If you eject faster, you don't have time. It freezes out at lower electron fractions, and that's what we see with the faster explosions, which are always the lower mass ones. So we get the first peak of the R process for the lower mass ones, and we don't get that for the more lugubrious, slower evolving, but more energetic explosions. More energetic is not faster necessarily. So it's the speed and the fight between the neutrino, anti-neutrino absorptions on the material that starts neutron rich but is being pushed up gradually. If you eject fast, it'll freeze out at low values. If you eject slowly, it won't, and it'll go proton rich. The rapid rotation with magnetic fields may eject it really fast. We haven't done that. But rapid rotation may not be very common. Collapsars, well, long soft GRBs are less than 1% of massive stars, maybe even 0.1%. And we're focusing on the 99%.
Okay, all right. Well, thanks again for the lecture.
Okay.